Recording. So today, chapter 6, 6.1 to 6.4. So let's do this. So I'm going to introduce state. So what exactly do we mean? What exactly do we mean? I think this is important, actually, to have this disclaimer here. So stateless and stateful programming are often called declarative and imperative programming respectively. The other terms are not quite right, but tradition has kept their use. Declarative programming, taken literally, means programming with declarations, saying that what is required and letting the system determine how to achieve it. Imperative programming, taken literally, means to give commands, to say how to do something. In this sense, the declarative model of Chapter 2 is imperative too, because it defines sequences of commands. Um, the real problem is that declaratives are not an absolute property, but a matter of degree. And that's a very good point, right?
Yeah.
So the language Fortran was the first mainstream language that allowed the writing of thematic expressions in syntax that resembles mathematical notation. This is definitely declarative in comparison to just getting the addresses in assembly to do the addition. So it is. So like I never thought of that in this way. When you have an A plus B in a programming language, such as C, even though that is we see that as imperative because we know that that's going to be compiled to like a memory address location, reading that the contents of that, reading the order and doing the sum. That's more online, but that's still better than doing that literally, which means that there's still some level of declarativeness even in that.
Yeah. Like you have to figure out if okay, is this an immediate constant that I'm adding? Am I getting this from a register? Is it on a stack? Is it somewhere on the heap? Like you have
Right.
to
So
think about all that stuff if you're doing assembly.
yeah, if you're going full pedantic, this is more like okay. So we need to accept the reality that declarativeness is a matter of degree, which is a very good point. The book sticks to the traditional usage of declarative as stateless, imperative is stateful. We call the computational model of chapter 2 declarative, even though later models are arguably more declarative since they are not since they are more expressive. Well, actually, not really, because the definition of declarativeness that we used has nothing to do with popular convention. The book established a very particular and precise definition of what that means, and so there's no reason to make this confusion. But well, we stick to the traditional usage because there is an important sense in which the declarative model really is declarative according to the literal meaning. Yeah, so we are kind of like bending ourselves to the traditional usage just to for us to agree that the declarative model really is declarative according to the literal meaning. This sense appears when we look at the declarative model from the viewpoint of logic and functional programming. And then there's like perspective, which I also think is interesting. So a logic program can be read in two ways, either as a set of logical axioms or a set of commands. This is summarized by Kowalski's, I don't know how to say that,
Kowalski.
Kowalski famous equation program equals logic plus flow. The logical axioms, when supplemented by control flow information, give a program that can be run on a computer. I don't see a logic program as a set of commands in any manner. So maybe this is I need to go to section 9 to see that.
Well, it kinda is if you think about if you think about a predicate call as a predicate as being a procedure that takes some arguments which and performs some bindings, right?
Yeah, but that's not what I'm writing. That's what is going to happen when I compile the program, right? Right,
The
but I'm
point
not.
is that
But I'm
the
writing
point is
it
that the point is
very.
that those are two complementary views of the same thing.
Yeah, but one of them is on your face. You're writing the axioms. On the other one, you have to think about it. That's not exactly the same thing.
Well, if
That
it
it's the
were the
same
same,
argument that why A plus B in C can be seen as declarative. Because just looking at it, just writing it, it is declarative. It's only not declarative when you think about it, what happens under the hood. The same applies here. No? It's the same thing. So you have to think about it to actually go to the set of commands understanding. Like I have to think how that's going to be implemented anyway. And if you're going to do that, then this argument also falls into the same trap. So to me, it's more like, okay, I understand what is being said here. I just see that they're not on the same plane of existence. One of them you have to think about it. The other one is in your face.
Uh, okay, what's the semantics of a predicate body in Prolog? Specifically Prolog, not general abstract logic programming.
Or the body, the semantics is that all of those axioms in the body needs to be true.
I don't know, I'm talking about, well, that is implied by the operational semantics of a body of a predicate in Prolog. But that's not quite what Prolog's um, that's not the only thing that it means, is the point, because Prolog acts also by as part of the language definition. It gives you an order of evaluation, essentially, right? It says it's depth first, and that's the control information that you need to interpret the program as a set of commands.
Yeah, but that's implementation detail. That's not
No, it's part of the Prolog standard, actually.
that's that doesn't deny what I said. Being a standard or not doesn't mean it's not an implementation detail that the order matters. I'm
No, no,
still
no. The
writing
order,
the axioms
no, no.
itself.
Well, the order matters if you're going to interpret those axioms as Prolog, right? Specifically.
Okay, so let me see if I understand your argument. The argument is that if you take an abstract point of view, then it's only a set of logical axioms. But when you have to implement this magical abstract machine into a computer, then you need to take into consideration the semantics of the operational portion of it.
That's close, but it's not quite what I mean. Because this paragraph is talking specifically about a logic program, right? A program is written in a particular language, and that language has rules that tell you how to execute it, right? And Prolog in particular, it defines the order of the predicate calls in the body of a predicate.
And the order criteria is exposed to you when you're writing it. That's why this matters, I guess. Because if it
Yes.
if it didn't, then it would be completely declarative, right? It would just be a what. But the
Yeah.
fact that you can have control over the order, that's why you can now see that okay, you have control over the order, so it is a sequence of commands now, because the order is exposed.
Yes. Um, if you go to a different logic language, then the rules of the order in which the execution happens may be different.
Maybe not matter,
Like,
maybe.
yeah, like Mercury, for instance, because it's a pure language, it is actually free to reorder some of the clauses in some situations, right?
Okay, now I see. A functional program can also be read in two ways, either as a definition of a set of functions in a mathematical sense, or a set of commands for evaluating those functions. As a set of commands, the definition is executed in a particular order. The most popular orders are eager and lazy evaluation. Yeah, so this is also the same thing. So uh, because you have control over the order, right? For example, in Haskell you can use the bangs to control if you want to actually have eager behavior instead of the default lazy behavior. Because you have control over that, you can see that as a set of commands for evaluating those functions. When the order is
It's
known, the
actually
mathematical definition can be run on a computer. Go on.
it's actually a little bit deeper than that because just by choosing Haskell as opposed to another language, you are already influencing the order, right?
Yeah, but I don't have control over the order just by doing that. I can just assume the default, right? And especially if you're going lazy as default, you don't know the order. You know the strategy, but you don't know the order. So, well, um, no, anyway, so let's continue here. However, in practice, the declarative reading of a logical functional program can lose much of its what aspect because it has to go into a lot of detail on the how. IO, for example, right, in Haskell. For example, a declarative definition of tree search has to give almost as many orders as an imperative definition. Nevertheless, declarative programming still has three crucial advantages. First, it is easier to build abstractions in the declarative setting, since declarative operations are by nature compositional. Second, declarative programs are easier to test, since it is enough to test single calls, give arguments, and check the results. Well, that's because we are using the second, well, the book's meaning of declarative, which means pure. In that sense, yes, of course. Testing state of programs is harder because it involves testing sequence of calls, which is well, the opposite conclusion of declarativeness. And third, reasoning with declarative program is simpler than imperative programming because, again, because of being pure, which allows you to use algebraic reasoning and verification transparency, so it's easier to think about it. And then we go to a very interesting separation between implicit declarative state and explicit state. Like, because we are exploring the term explicit state, why we are calling explicit. So what is a state? A state is a sequence of values in time that contains the intermediate results of a desired computation. So let's think about it. Imagine that you have a fold, but instead of you're using a recursive function to do the accumulation, and you're accumulating the sum of things, and then if you write it down on a piece of paper on your text editor or on your brain, the sequence of the input versus output, the output being the accumulator, these
Um,
progression.
that's actually not even input and output. Those are just the two arguments in each recursive call.
That's fair enough, but it's gonna be look the same. That's true though. This is XR and this guy, right? So
Yeah.
this and this. Um, yeah. So if you pass this input and these two inputs for some list function, this is the sequence. This sequence is a state, and this is a very interesting way to look at it because I never understood, but maybe I never thought about it that way, that the sequence will be the state. And I would argue that most of the time you don't care about the sequence. You care about something else that also is history sensitive, but not about the transitions, not about the inner like okay this happened and that it was like this and now looks like that. That those two nodes usually don't store them. You store only one, which is the final one. So it's very interesting to point out that you can interpret the sequence itself
Um,
as a state.
well, the reason you think about that is because you're thinking about the current state, which is different from the entire state, which is the full history, right?
Yeah, no, but that's what I said. Usually that's not useful to look at from the beginning to the end on that holistic view of like, okay, I'm gonna actually store. Uh, well, I should point something out. That's usually not useful if you're not talking about event-driven systems, I guess. Because if you are talking about that, then people like to store every event, including the first ones from the beginning.
But the event is not a state per se, right? It may cause a state transition, but it's not itself a state.
Yeah, exactly. But that's usually the argument why they need to save all of them.
By the way, Lemus, this definition of a state is a sequence of values. This is actually part of the inspiration that led to closure and atomic, because an atom, for instance, in closure,
Yeah,
it
you can
embodies
roll back.
exactly that.
Yeah, you
Yeah,
can roll back.
and
Uh,
atomic actually does store the entire history. That's kind of the point, right? It's an immutable database with a mutable
no, but
view
that's no, no,
over.
no. But that's the thing. That's a database. That's a single blob that you store the history of that blob. Here you may have a sequence of many blobs, right? A lot of things may be happening at the same time. The database has a context in which makes sense to be understood as a single thing. That I understand. It's like the accumulator here. It's going from 0 to 1 to 3 to 6 to 10. If I want to know that I went from 6 from 3 to 6, fine. That's completely understandable. But the definition here is the sequence of including everything. Like this
Well, yes.
this thing.
Well, yes, because this is like if you think about the state across time, then you have to include everything. That's kind of what this is getting at.
Exactly. And I was kind of thinking, okay, how would I use that? That I need to know the transitions of everything, not only what I care about. For example, um, Lyceum. We implemented something called game state. The game state doesn't know what was the second to last key on their keyboard that you pressed. It doesn't know that because it's not useful
Well,
for us. But according to this definition, if we're going literally, we would know that.
well, not really, because the key press is not part of the state. It's an event.
No, but it
I mean,
matters
you
for the
could.
state. It definitely matters for the state.
The
We
point is
even
that
we
it's
even
not.
store that. We store which key binding you press last to know what we should do with it. We just don't care about the second to last.
Mm, well, that's fair, actually.
So yeah, uh, that's why when I read this, I was like, the sequence is a state. I was like, okay, like if you're talking about rollback operations and like databases and transactions, fine. But in a
Mm,
general sense,
well, closure, as I said, the stateful features of closure, they were actually based on this idea
no,
that.
I believe. I believe. I'm just saying that weird. That's what everything I want to say. So we are calling this implicit state because the the act of understanding this sequence is not being done by via the language. It's done by your mind. So that's why we're calling implicit. An explicit state is a procedure. In a procedure is a state whose lifetime extends over more than one procedure call without being present in the procedure's arguments. Because if it is present in the procedure's arguments, we go back to the original problem of like, okay, I want to extend the state. Good luck. Now you have another output and another argument for the recursive call. So we're going to break everything.
Yeah,
So that's the
yeah.
thing. We're going to introduce a cell, which as far as I can tell is pretty close to Clojure's atom semantics.
It's basically an atom, except for some reason their primitive mutation is
Exchange.
exchange
Yeah,
instead
which
of
is
compare and
weird,
swap.
right? Like, that's weird. And the expression based thing returns the old stuff, which is also a very controversial decision.
Some low-level languages do that, and that makes like swapping the values of two variables easy. But I don't see the point of doing that in a high-level language, to be honest.
Explicit state cannot be expressed in a declarative model. To have it, we extend the model with a kind of container we call a cell. Declarative model extended with cells is called the stateful model. And then we have the same example as before, but using the atom, right? Using the cell. So you create a cell which is local, and then you
Right,
keep.
this is the instrumentation example, right? You want to count how many times you're calling a function
Yeah,
without changing the interface.
yeah. This is the same definition as before, except we define a cell and update its content in some list. And you don't have to break the interface. That's kind of the big deal. The ability to have explicit state is very important. It removes the elements of declarative programming. With explicit state, abstract data types gain tremendously in modularity since it is possible to encapsulate an explicit state inside them. The access to the state is limited according to the operations of the abstract data type. We're going to explore this data type thing today still, so there's more to talk about it. This idea is at the heart of OOP, a powerful programming style that is elaborated in Chapter 7. So now, state and system building. So we're going to talk about the principle of abstraction. So the book is defining abstraction as composed out of two parts, specification and implementation. So specification is essentially the contract, which is how everybody else is going to interact with it. So this is the interface, this is the API. We call this the specification.
This is the signature in OCaml land.
Exactly. And then we have the implementation, which is how you're going to make it happen. And the main difference, like using the previous book that we read, the patterns of the software, Focusing on making one of those shoes the simplest defines which school you're going to be, in essence. The miraculous property of the distinction specification implementation is that the specification is usually much simpler to understand than the implementation. Yeah, this is well, this is not a universal agreement. We like to believe so, but some people disagree. One does not have to know how to build a watch in order to read time on it. This means that it's possible to build a system as a concentric series of layers. One can proceed step by step, building layer upon layer. At each layer, build an implementation that takes the next lower specification and provides the next higher one. So this is essentially how you make functions that use functions that use functions. That is an example of that. Systems that grow.
Yep.
How is this approach supported by declarative programming? With the declarative model, all the system knows is on the outside, except for a fixed set of knowledge that is born with. To be precise, because the procedure is stateless, all its knowledge, its smarts, are in its arguments. So like the function, the component is dummy. It's a combinational box. It's essentially a mechanical box. It doesn't have memory, which means that you need to provide the all in its arguments all the data to do its calculation.
Yep.
The smarter the procedure gets, the heavier and more numerous the arguments get. Declarative programming is like an organism that keeps all its knowledge outside of itself. So it's a combinational box. Despite his claim, well, this is just a curiosity. Chapter 4 partially alleviated this problem by adding concurrency. Stream objects can accumulate internal knowledge by their internal arguments using the difference lists. Chapter 5 went further by adding ports and port objects. A port object has an identity and can be viewed from the outside as a stateful entity, which we used for doing some fun stuff. But
Yep.
this requires concurrency. In the present chapter, we want to do the same without concurrency in sequence. There is a total order among all operations in the system. This cements a strong dependency between all parts of the system. Later in chapter 8, we will add concurrency to remove this dependency. The model of that chapter is difficult to program in. Yeah, so declarativeness, declarative concurrency is easier to reason with than stateful concurrency. Makes sense.
And message passing is easier to reason about than explicit state in a concurrent
Uh,
setting.
yeah, the book. I don't know where we're gonna reach that, but the book points out that some people understand method calling as message passing, and I feel the book thinks that's weird, and I also agree. If you don't do the implementation, which is not record based, it's message based, that just doesn't make sense, and I agree with that. So system properties, I think we're gonna see that in here anyway. So
I guess the main point is that it's comparing like a traditional method call with a request response cycle, but that's not really a single message pass, it's a pair of message passes, right? That's why it's weird.
I don't see the message. That's kind of my thing.
The
The
message is the method label plus the arguments.
But why are we? What is the gain of looking at it as a message pass instead of a function definition?
Well, no. It's not a function definition.
A
It's
function
the
call,
method
sorry.
label. It's not really. Well, the gain is that you can think about it as you can abstract over the arguments basically. You can treat it as a data structure in some sense.
I don't see it. I don't see it still. A data structure.
Like because normally when you do a method call, you're saying, okay, I have this method in this object. I'm passing some arguments to it, and then I'm waiting for the return, right?
That's the same question I do for a function.
But if you think about it in terms of message passing, you can say, okay, no, actually, I have this object and I have this message that I'm sending to it, and that message is is a record with a particular label and some data inside of it.
Mm-hmm. So far, I'm still asking the same for a function. So
Well, yes, because there's some deep lore in there if you go back to the Lambda papers, because like as a curiosity, Scheme actually was originally intended as a way to explore the actor model, which is all about message passing, right?
Mm-hmm.
And then they realized at some point that, oh, actually, the code to handle message dispatch and the code to handle function calls is identical. So let's get rid of actors and just do procedures.
So that's the reason. It's because they
Yeah,
understood that the message passing implementation and the function call implementation they look the same, which makes sense in a grand scheme of things. And then they decided to just unify it with a single
yeah.
concept. Now that makes
And
more sense to me.
yeah, note that this only makes sense if you are talking about synchronous calls, right? Request response. If you're talking about async, that's slightly different.
That's slightly different. Yeah, but at least now I understand because the book says like people has this convention, but I felt that the book was not agreeing with it, and I was like, okay, I'm on your side. System properties: encapsulation, compositionality, and instantiation. So encapsulation is about hiding the internals of a part. Compositionality is about combining parts, and instantiation evocation is about creating many instances as possible with the least amount of primitives as possible. Um, the least amount of definitions as possible. So let's see. The properties do not require state. They can be used in declarative programming as well. On one hand, it is possible to use encapsulation declarative programs without state. We have already used it many times. And then we have invariants, which is very interesting. Encapsulation and explicit state are almost useful when used together, are most useful. Adding state to declarative programming makes reasoning about the program much harder because the program's behavior depends on the state. For example, a procedure can do a side effect. It modifies a state that is visible to the rest of the program. There is another way to justify why it's harder. It's not only because the program's behavior depends on the state, but that's because that's farther away from you.
Yeah, it's non-local.
Which means that when you, from the caller's perspective, when you're calling a declarative component, you have access to everything you need to reason about it, because you are the one providing the environment. But if you are dealing with a non-declarative component, there may be some hidden pieces that are farther away from the caller, which means that the reasoning is harder because it's scattered.
Yeah, at the end of the day, it's about locality.
Um, yeah, pretty much. So side effects make reasoning about the program extremely difficult. Bringing encapsulation doesn't make reasoning tractable again. This is because stateful systems can be designed so that a well-defined property called an invariant is always true when viewed from the outside. So for example, you may not know what is the value of the integer that is being held in the state, but you know it's always a positive number. So you can do something about it. This makes reasoning about the system independent of reasoning about its environment. This partially gives back one of the properties that makes declarative programming so attractive. Invariants are only part of the story. An invariant just says that the component is not behaving correctly. It does not guarantee that the component is making progress towards some goal. Yeah, so maybe it should not only be positive, but it should be within a particular range. But you cannot. So that would be the goal, but you only have the invariant of being positive.
Yeah,
For that, a second property is needed to mark the progress. This means that even with invariants, programming a state is not quite as simple as declarative programming. We find that a good rule of thumb for complex systems is to keep as many components as possible declarative. State should not be smeared out over many components. It should be concentrated in just a few carefully selected components. Okay, so this is a simplest version of a more general guide, which is don't just go as far as you need. Don't go overboard. So, for example, if you're making uh, if you're making a descriptive declarative program, you may create a data structure that is more complicated than it needs to be. That happened at work last week. We were doing something, and I was reviewing a PR, and my colleague made a descriptive program. He didn't know he did it, so I had to explain a little bit. And I said, but this descriptive program is more complicated than it needs to be. So that's basically a rule of thumb. Don't go overboard if you don't have to. So just try to work with the minimal amount of power as possible.
there's a corresponding principle, actually, not just a guideline, but an actual principle in the field of security, actually. It's called the principle of least authority.
Mm-hmm.
Basically, you should never give more authority to a process than it actually needs to do its job.
Exactly.
Otherwise, you're opening yourself for exploits.
These three properties define component-based programming. Um, Components can be instantiated. Yeah, but then we have there are some examples. So procedure abstraction. We have seen our first example of components in the declarative computation model. The component is called the procedure definition, and this instance is called the procedure invocation. Procedure abstraction underlies the more advanced component models that came later. Functors, which are the compilation units, we've seen this before when talking about modules. Concrete components, such as the messages with the port objects. In component-based programming, the natural way to extend a component is by using composition. Build a new component that contains the original one. A new component offers a new functionality and uses the old component to implement the functionality. Um, okay, so now OOP. So object-oriented programming adds a fourth property. So we already have encapsulation, instantiation, and compositionality. We're gonna add inheritance. It is possible to build a system in incremental fashion as a small extension of modification of another system. At first glance, this seems kind of redundant because the way it's written, what is the fucking difference between this and compositionality? So let's read a little bit more. Incrementally built components are called classes and their instances are called objects. Inheritance is a way of structuring programs so that a new implementation extends an existing one. The advantage of inheritance is that it factors the implementation to avoid redundancy. Compositionality does the same. But inheritance is not an unmixed blessing. It implies that a component strongly depends on the components it inherits from. This dependency can be difficult to manage. Although component-based composition is less flexible than inheritance, it is much simpler to use. We recommend to use it whenever possible and to avoid inheritance only when composition is insufficient. And I think this is my first disagreement. I think it's the opposite. Inheritance can be more convenient than composition, but composition is definitely more flexible.
That's yeah, that's actually just your impression because the truth is that composition and inheritance are actually the same thing.
Well, I
Or to
agree.
be or to be more precise, inheritance is a particular form of composition. There's a nice paper about that I read recently, and I actually posted it on the server.
Mm-hmm.
That explores, okay, how do you implement an object-oriented, an OO system in the context of a purely functional language?
Yeah,
Like, what's
we
the
I saw that paper. I didn't read it. I read it fully. But the book is making a difference. The book is making a distinction. It's naming it a fourth property. So I am treating it as such, as a separate thing. And being a separate thing, I disagree with this statement. I don't see how
yeah,
composition is less flexible at all than
well,
inheritance.
composition, it cannot be because it includes inheritance. Inheritance is a form of composition. I agree.
No, but you're disagreeing even further because you're saying that there's no fourth property. Essentially, the book is saying there is. You're disagreeing on a more fundamental level. My disagreement is if inheritance is a separate thing, it is not more flexible than composition. Um, so let's go. Declarative model is explicit state. We need to go. No, we're still okay in time. One way to introduce state is to have concurrent components that were indefinitely and that can communicate with other components like the stream objects and the port objects. In the present chapter, we directly add explicit state to the declarative model. Unlike the previous chapters, we're not going to talk about concurrency. Explicit state is a pair of true language entities. The first is the state's identity, and the second is the state's current content. There exists an operation that, when given the state's identity, returns the current content. This operation defines a system-wide mapping between state identities and all language entities. What makes it stateful is that the mapping can be modified. Interestingly, neither of the two languages entities themselves is modified. It is only the mapping that changes. So I have a question.
Okay.
So this means that Oz implements statefulness by swapping the mapping and not rewriting the memory. Is that it?
I mean, rewriting the memory is a machine-oriented view of saying that you are changing the mapping.
No, it's not. Because in one way, you are literally going there and rewriting it. In the another way, you change the mapping and you let the garbage collection get rid of it. Those are completely two different strategies.
Uh, well, I guess a different way to put it is that this is a formalization of the idea of having an addressing memory that you write. Because what you want to do, ideally, is say, okay, I have this model that I'm using to reason with about my program, right? And I don't want it to talk about machine details because, like, that's more of a concern for the implementation of the language, not really for someone using the language who wants to reason about it, right?
No, I agree that that's a formalization on it. But as far as my understanding goes, and maybe I'm wrong, is that what Oz is doing is by changing the mapping, they don't need to care about the abandoned value because it's going to be
Garbage
caught.
collected, yeah.
It's going to be caught by the reachability algorithm and it's going to be garbage collected. So they are
Yeah,
just doing
that's.
that. But to me, there is another approach of just going in there and rewriting it. You don't
I
have to
mean,
wait for
that's
the
a.
garbage collection.
I mean, that's kind of effectively the same thing because if you think about a more implementation view, how would you do this? You would say, okay, here's a cell. It has an address which is mapped to its name in the formal model, right?
Mm-hmm.
And that works because the address is unique. It can change as the garbage collection moves things in memory, but logically you don't care about that. You just care about the fact that it is what it is.
Yeah, but this we are not talking about logically only. We are talking about the kernel language. We're talking about
Yeah, yeah.
what are we going to be using for the operational semantics. And as far as I can tell, OS chose the path of just exploiting the garbage collection.
No, no, no. And then you say, okay, what does the memory address point to of this mutable cell? What is its content in memory when you're going to actually implement it? And you say, okay, uh, it's a memory cell, hence the name cell, right? Very creative.
Mm-hmm.
That just contains a reference to some other language entity. Like it could be a functor, could be a procedure, could be a number, could be whatever, any value, right?
Mm-hmm.
And then the operation of mutating the cell just goes to the address that it points to, changes the reference that's in there, which means that the previous reference now is that was there before is now unreachable because it's not in the cell anymore, right?
Yeah, but you're not going to do anything about it. From the perspective of the implementer of this feature, you don't need to care.
Yeah, you don't. You rely on the.
On the another
Yeah, you
folk
rely on.
that implemented the reachability and the garbage collection.
Yeah, you rely on the garbage collection to do the cleanup. If the previous value is still referenced somewhere, it stays because it's referenced. Otherwise, you get rid of it to free up memory. You are correct on that.
Oh wait, so that is the reason. Actually, we just the reason is obvious. The reason it just doesn't override it is because the semantics allows for somebody else to be looking at it, which means that you cannot just override it. That's the reason. So if you are doing a C1 and a W, and I'm changing C1 to Z, somebody else may be using the W, so I don't have the permission to override the W in place myself. I
Yeah.
have to rely on the reachability because otherwise I may be fucking somebody else.
Also, the W may be immutable, so there's that.
Yeah, but no, this was a dumb question from me. It makes perfect sense they decided to go this route because you need to allow other people. Well, you need to not. You need to disallow people fucking each other, essentially.
Yeah, that's why the closure reference types are the way they are. They are single mutable cells that you put an immutable value inside of it most of the time.
Mm-hmm. No, it makes perfect sense. And then we have to go to the implementations of the cell. I'm not going to go through details here, but we are adding two new things, which is the new cell and an exchange. The exchange atomically bind X with the old content of C and set Y to be the new content. So you have a way to like not lose what was there, essentially. And
It's still kind
then,
of weird that they chose this primitive and not something like compare and swap, but okay.
yeah, that's very weird. Well, maybe that's the reason, because if they were using compare and swap, they would be using three primitives, not two.
Right, because for compare and swap, you need the compare and swap itself, you need the read and the unconditional write as three separate primitives. Which is, in my opinion, that's a bit cleaner. But, well, for minimalism, exchange definitely wins.
Yeah, and then you may look when you read this, you notice that this is the same shit that we did for ports and messages.
Yeah.
Obs and readers will notice that this semantics is almost identical to that of the ports. The principal difference is the type. Ports are identified by a port name and cells by a cell name, which, as far as I can tell, is the same shit, just a different region of the that we are storing the things. Because of the type, we can enforce that cells can only be used with exchange and ports can only be used with send. So like we are making nominal types for them because we want these two things to be exclusive, but probably they are the same. I wouldn't be even surprised that there's only one module for both, like one implementation that works for both, and we just make the wrap and unwrap from the outside, but they are using internally the same thing.
I mean, you could do that if you wanted. They probably don't for performance reasons, right? Because those indirections, they are not free. But you could do that, indeed.
What do you mean these indirections?
Because when you do a wrap and unwrap, you're
Ah,
basically
okay,
building an opaque thing that has something else behind it, right? That
okay,
adds a level of indirection.
that's fair. Blah blah blah. Relation to declarative programming. So, in general, a stateful program is no longer declarative. No shot, no shit. Since running the program several times with the same inputs can give different outputs depending on the internal state. And again, this is a much more useful definition of declarative, right? So this is very to the point. It is possible to write stateful programs that behave as if they were declarative, to write them so they satisfy the definition of a declarative operation. Yeah, Nathan brought this up years ago when we were making the Radiant game, and we were discussing about mutability, and then he said, just because a program has mutability doesn't mean it's not pure. It doesn't break the referential transparency. That's what he said. And at first I was kind of puzzled by like, okay, I don't understand that. But then he explained it exactly what this subsection explains, and it makes perfect sense. So if you're making the mutable stuff only within the boundaries of this, and it doesn't matter for anybody else, that's perfectly fine. And you can still use referential transparency with it. You can still swap it, um, because from the outside perspective, it's going to behave like a declarative component. So that means that you can have an array in a Haskell program, in a Haskell function, that actually does mutability from the in the function's body, but from the outside perspective, it actually behaves like a pure function. And there's even
Yeah,
a type
another
for that, which is called st. Go on.
yeah, another example of this is actually transient enclosure. Because like enclosure, you have immutable data structures by default, right? But maybe you have to build a very large data structure inside of a loop. And ideally, you would want to use mutation for that to avoid allocating a bunch of intermediate small things, right?
Mm-hmm.
So there's this notion of transients where you say, okay, starting from this immutable data structure, give me a mutable version that has a very similar API, but the operations are actually destructive. So I use those to build up my collection, and then at the end, I turn that back into an immutable collection and return that.
That's essentially what st does. That's in essence what st does.
Rock also does something very similar, but it does it automatically because it has reference counting, so it knows when the value is
Syntax.
unique.
Let's see if there's an example. Yep, there is an example. So looking at this is pure, but
Yep.
it's not. And that's kind of the huge deal of ST is that it allows you to, okay, I'm going to actually do a bunch of mutable things in the body of this, but I want to unwrap it, which is run ST, and from an API's perspective, you're good to go. You're definitely good to go. And you can even make a fold. Yeah, of course, you can even make a fold out of it.
It's easier to try to look for things that you cannot fold, right?
Yeah, exactly. Anyway, so ST, very educational. So it's the same thing. Another interesting example is memorization, in which a function remembers the result of a previous call so that future calls can be handled quicker. Yeah, but memorization has a separate problem, which is, um, well, I guess in this language doesn't matter because you need to have a reference to the table that you're saving, and that kind of runs the risk of destroying the magic of like the misleading API
Well, the
because you
whole
need to
point
give
here
me the
is
reference.
yeah, no, the whole point here is that okay, I can have the reference hidden inside of the implementation
Yeah, exactly.
of the thing in a local name,
Yeah, you
right?
can do
Using lexical
local.
scoping.
Exactly, you can use the lexical scoping to not to like already have the reference. You don't have to provide another one. You can keep it. Sharing inequality, very important. So sharing, we can make an alias, right? So we can have two identifiers pointing to the same cell. Change the count of x, also change the count of y. Um, when reasoning about a program, the programmer has to be careful to keep track of aliases. This can be difficult since they can easily be spread out to the whole program. We've seen this problem before with data flow variables. This problem can be made manageable by encapsulating the state, using it in just a small part of a program and guaranteeing that it cannot escape from there. Token equality and structure equality. So here we have structure equality. Then we have these. I think this is now the token equality example. So they are not going to be equal, right? Two cells are not equal
Right.
if they have the same content, right? They are equal if they are the same cell. And if you do something like this, they would be equal in terms of their content. And if you do something like this, then they are token equal. And then for the main course, we have 15 minutes to talk about 6.4. So in essence, this is analyzing the ways that you can abstract data. There are four properties that you can do this for. No, three because it's eight. So three properties,
And they are
and
binary.
they are
So you
binary.
have eight.
So yeah, so we have openness and security. We have if they are stateful or stateless, and if they are bundled or unbundled. So what do they mean? Open and security means what we saw in chapter 3 about capabilities,
Yep.
which means do you have the right to do this? Yes, that's the question that you're trying to answer. Stateless and stateful are very obvious. Are you using a cell or not?
Yeah, we just saw this basically.
And bundling and unbundling, how are those things aggregated? So an unbundled ADT is one that can separate its data from its operations. It is remarkable that it is a remarkable fact that an unbundled ADT can still be secure. To achieve security, each instance is created with a key. We've seen this before. An unbundled ADT can be more efficient than a bundled one. For example, a file that stores instances of an ADT can contain just the data without any operations. If the set of operations is very large, then these can take much less space than storing both the data and the operations. When the data is reloaded, then it can be used as before as long as the key is available. So I should actually rephrase that. How are the operations and the values aggregated? That's basically the main thing. Yeah, so a third choice to make is whether the data is kept separate from the operations or whether they are kept together. So if they are kept together, uh, you are closer to an object. Not necessarily an object, but you're closer. And if you add state to it, then you have an object.
Yeah, kinda.
Yeah, so variations on a stack. So you're going to implement a stack using these multiple strategies. So open declarative stack. So stateless and open. So no security. So here we have it. We have a bunch of functions, right? It's open, which means that you can exploit that you know that the stack is a list and use list operations on it. And here you have the pop. The version is open, declarative and unbundled. So now a secure declarative unbundled. So how do you do that? You add the wrap and unwrap operations. So you have to provide the key for it.
Yep.
Well, actually not really. You don't. It's not that you have to provide a key. There will be a key. Okay,
And
I
it's
need to
hidden
remind
inside of the
myself. Yeah, the
yeah,
programmer
the
doesn't have
keys.
the key.
Yeah, only the operations have the key.
Exactly. So this is how you do unbundled, declarative, and secure. Now we go to secure, declarative, bundled, which means that we are essentially this is so crazy. We are creating an aggregation using a function.
I mean,
We are returning this. No, actually, this is the record is doing the magic, right? I take that back. This is creating a record
no,
that
it's
contains the things.
yeah, actually it's the lexical scoping that's doing the magic, right? Because the whole point of this being bundled is that you can't really separate the push from the stack that you are pushing into, right?
Yeah. Yeah, but not only the access scoping, but some sort of data structure to aggregate the
Yeah,
things.
yeah. You need to have some sort of collection to put all the things together, right?
Exactly, and that's how it's going to look like. So you create a new stack, and that will give you an S1, which is going to be the record, and then you just use the dot notation to get the things. But because this has higher order programming, which the records can be functions, who cares? Uh, so now we have a secure, stateful, bundled, which means that we're going to use a cell to do the things, and the operations will happen on the cell, and you're not going to have access to it, so it's already encapsulated as well. And it's also using the record to aggregate them, to bundle them.
Yeah, the fun thing is you don't really need the wrap unwrap pair if you're doing the bundling because you just use lexical scoping for the
Yeah.
security.
The lexicoscoping is serving as the security layer on here. Uh,
That's very neat.
that's not true, because you can still do a but these are not returning the full contents of the cell. That's why this works. But you can still exploit the fact that this is a list from outside.
Can you?
Yeah, because well, not in this case, because in this case we're not exporting the stack. The push is a like a mutable version of it, which means you are not returning the stack for the guy calling the push. You're starting only for yourself. Then that makes it secure because this means that the list implementation is still unattainable from the caller. You don't know that. Yeah, so I take that back. This is still secure because you're not providing. There's no way to get the stack. You can only push to it, remove elements to it, and ask if it's empty or not. If that's the case, so far so good. I thought that the push would also give you the stack, right?
Nah.
Uh, because this is kind of a useless stack if you think about it. You can only push and pop to it. You cannot do any inspection.
I mean, the pop returns the value.
Yeah, but
Um,
what if I want to know how many are there? What if I want to know which one is the one below the top? There,
well,
like this
this is
is
a
not
very,
this.
I mean, this is a very strict stack discipline, Lemos. It's strictly last in, first out, right?
Yeah, there's not even a top function.
Well,
Uh,
pop is kind of pulling double duty here because both removes an element and returns it, which is, I don't particularly like that, but well,
uh, yeah, but in a more like rich stack discipline, you need to be careful to not tell the guy that this is a list, because if you tell him, then you're fucked.
yeah,
Fucked in the sense that
that's
he will be able to exploit list functions.
actually more important than that is the fact is you shouldn't expose the mutable cell actually, otherwise all bets are off.
Yeah, you should not return C ever. Comparing two popular versions. So let's compare the simplest secure versions of the declarative and stateful models. Each of these two versions is appropriate for security DTs in its respective model. It pays to compare them carefully and think about the different styles they represent. In the declarative unbundled version, each operation that changes the stack has two arguments more than a stateful version, an input stack and an output stack, as you may expect. The implementations of both versions has to do actions when entering the existing of and exiting an operation. The calls for of unwrap and wrap corresponds to calls of these respectively. The declarative unbundled version needs to know higher order techniques to work with many stacks, since all stacks work with all operations. On the other hand, the stateful bundled version needs instantiation to create new versions of push, pop, and is empty for each instance of the stack ADT. That's true. The declarative unbounded version works with any stacks. The stateful bundled versions, they are married to a single stack.
Yeah, you can never take a pop from one stack and use it on another. That's just flat out impossible.
Here's the interface of the declarative unbounded version. Here's the interface of the stateful bundled version. In the stateful bundled version, we define the stack type this as that. Okay, secure stateful unbundled. So this is essentially using a cell with wrap and unwrap.
Yep.
And there you go. And there you go.
Yeah. For some reason nobody does it this way, but you could, and it's actually kind of neat.
Yeah, but this one is not secure.
It is.
It is. Are you sure?
Because the programmer doesn't have the key. Only the methods
Ah, no,
have
no, no.
the
Sorry,
key.
sorry, sorry, sorry. I said it wrong. It is secure because it's using the wrap and the unwrap. No, yeah, I take that back. It is definitely using that. Definitely secure. And then we go to revocable capabilities, which is very neat because it means that you can revoke somebody's right to do something. Because we saw capabilities, which is the right to do something. But now we are seeing how you can get that right removed. So revocable, you can make an object revocable and you are granted two operations, which is the one R object, which is essentially does the normal stuff, and if you call R from that point onwards, nobody's going to be able to do R object again.
Yep.
And you are doing that by overriding the cell with a proc that raises an exception.
Yeah. And the point
And
here
there's a
is
problem
you
here.
can. Well, what's the problem?
We are missing an argument here, no?
No, because this is in expression position, so the argument is actually C.
So the C is going to be the R object.
Yeah.
Okay, thank you.
Yeah, and the point of here is, okay, since you now have a revocable capability based on a more primitive unrevocable one, you can share the revocable version to somebody else, let them do their thing, and then revoke it so you are sure that they will only do their thing and not anything else after that.
Oh, you mean that if you have a more general, more powerful thing, and then you create the more powerful, and you start removing shit.
Yeah, like
Uh,
if you. The whole point here is you have a general way to take an arbitrary capability and make it revocable, right? And why do you want to do that? Because you may want to share your capability, but have the ability to take it back later, you see?
no, but I'm talking about an object that can do multiple things. Like, so let's say that a particular object is capable of calling 5 methods, but my partner should only have access to 2 of them. So I can create an object with 5, and before passing to him, I revoke 3 of them.
You would. Well, actually, the way to do that would be to create a new object that has only the two methods that you want to share,
That's true.
and those two methods call to the one that you have with the 5.
That's another way to do it, and a better way, I guess. Cool. Okay, now we go to parameter passing, which is very cool because I was not aware that like of all of these. Some of them I have my questions on their usefulness. Let's go. So now that we have mutability, like statefulness, which essentially means that you can mutate things. Now it matters to talk about this because at first glance it seems kind of random. Why out of nowhere we're talking about parameter passing? Because now that you have an explicit stateful model, that means that the way that the arguments are going to be treated matters. Because before they were always the same thing. There's only one choice. Now there may be multiple choices. Um, so let's start by call by reference. The identity of a language entity is passed to the procedure. The procedure can then use this language entity freely. This is a primitive mechanism used by the computation models of this book. Imperative languages often mean something slightly different by call by reference, which is true. They assume that the reference is stored in a cell local to the procedure. In our terminology, this is a call by value where the reference is considered as a value. When studying a language that has call by reference, we'd recommend looking carefully at the language definition to see exactly what is meant. So in imperative languages, when you say that something is being done by call by reference, you mean a pointer.
Yeah.
So you mean a direct access to the memory region that is storing your data.
Yeah.
Here, we have a different terminology for that. Because here, call by reference means the language entity, which in this case is its name. Because we have a single store thing, single assignment store, which means the names need to be unique. Which means that the name is enough. I shouldn't remember. What happens if you do shadowing in this language?
Shadowing works as you would expect.
Oh, but then,
The point here is
okay, if you
that
do
if you
shadowing,
have,
the language identity is going to be the closest one.
yeah, the closest one.
Okay. Okay, so it's not single names, unique names. Well, it is in the internal machinery, but from the programmer's perspective, it's going to be look the same, I guess. Call by variable. So this is a special case of call by reference. The identity of a cell is passed to the procedure. So you have the Pascal version of it, which apparently has this syntactical element. We code this example as follows. So essentially, you are receiving a cell which is working as a pointer, and we dereference the pointer and we multiply and we reassign the pointer to it. So essentially, the call by reference in imperative languages is called by variable in here, right? No,
Yeah,
it
you're
says it's called by
basically,
value, so I got that wrong.
well, that's because what's happening there in call by in the quote unquote call by reference using the common terminology is um, you have a local variable in the body of the procedure that you can mutate, but that local variable contains a pointer to something else. You see?
No, could you repeat that? You're talking about this phrase, right?
Yes.
They assume that the reference is stored in a cell local to the procedure.
Yeah, because if you take a parameter a that is
Mm-hmm.
being passed quote unquote by reference,
Mm-hmm.
you can rebind the a locally, but that doesn't actually mutate the object. It mutates the a that you have locally in your procedure.
Mm-hmm. And what is the difference with our stuff here?
This is called by variable, which is slightly different actually. Here the a is coming, the variable a is coming from the outside. So if you mutate it here, it's visible when you return.
But isn't that also the case with quote-unquote call by reference in imperative languages? Like this looks exactly the same as it would in C.
No, because there's a difference between you take a pointer which has a name, you rebind the name locally, versus you take a pointer and you mutate the thing that is being pointed to.
I don't understand. If you have an int x equals 0 in C, and you pass to sqr the address of C, my bad, you can just mutate the value of the 0 to be something else.
Yeah, but that's if you mutate the thing that is being pointed to by the pointer. That's
Exactly.
different from mutating the binding, the local binding that contains the pointer.
I don't see. I'm having a hard time.
Look,
To me,
scroll,
this is
scroll
like
down,
almost
scroll
a
down
one-to-one to C.
no, no, scroll down to call by value, okay?
Call by value.
Yeah,
Okay, so
yeah.
in here
See,
you're creating a local one. You're creating a local
yeah,
one, and then you are mutating that local one, and then yeah, that's not what people mean by call by reference in C at all.
no, 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 no. There's a difference. Okay, let's try to. If you take a pointer and you pass it to a function in C, okay?
Uh huh.
That pointer is going to have a local name, right?
Uh huh.
What happens if you mutate that local name to be a different pointer?
In C,
Yeah.
so you have a pointer with a particular name in your that you're receiving as an argument.
Yeah, like, let's say you take an x which has a type pointer to int, And inside of your function, you do x equals whatever. What does that do?
It's been a while since I did C, but that would change the address that is being pointed by X, no?
Yes, and that's different from mutating the value that x points to.
Oh yes, you need to dereference it. Like you
Yeah,
need
you need to
more
do.
syntactical elements to do that difference. I understand.
Yeah, yeah. In order to mutate through the pointer, you do asterisk x equals or whatever the
Exactly,
proper syntax
exactly,
is in C,
exactly.
right?
It is asterisk equals.
Yeah, when you do the asterisk equals, you're doing the pass by variable, basically.
Ah, okay. So call by value, me, or call by variable.
Which is the one above where you take a variable, you mutate the variable, and that's visible from the outside, right?
Ah, okay. So because in C we would have to dereference the pointer, that's why it's not called by variable.
Yeah,
I
it's
see, I see,
yeah.
I see, I see. Tiny difference. Very tiny, but okay.
Yeah, no, these things are very subtle. These things are very subtle,
Yeah,
but they're
yeah.
important.
Okay, so okay. Now I understand why this is not the C version. And I guess wait, what was the comment? In our terminology, this is called by value, where the reference is considered as a value. Call by value. As the
Yeah,
and the reference is
because
considered as the value.
yeah, because
Ah, now I understand. So you're
yeah,
essentially
because
saying that, okay, I have this address, I have this reference, make a cell out of it, and then this is mutating what the reference is pointing to.
yeah, that would be in our example, this mutation of A would be x equals whatever without the dereference, you see?
Without the reference. Okay, now I see. Yeah, subtle as fuck. Okay, so we have call by reference, which in this book means the language entity, which is in this book, in this case, it's name, the name. Then we have call by variable, which means doing the assignment of a variable directly and that being looked at elsewhere, that has an effect elsewhere. Um, I understand that the practical subtle differences that makes call by reference in C the call by value, but I think what C programmers would identify themselves with would be this code, in my particular opinion. So if you look, if a C programmer looks at this code, he will feel at home looking at it because you're creating something from the outside and you are and a function is altering that and you notice the change of C after calling the function. So this is why I think a C programmer would feel at home looking at this.
Yeah, no, a Python or a Java programmer would look at call by value and be like, yeah, that's totally call by reference.
Yeah, and then a Python person may have a different opinion, but I think the C people would identify themselves with this one.
Yeah, no, the C people would totally think of call by reference as call by what the book calls call
Call
by
by
variable.
variable. Yeah. Okay. So but again, we are looking at the details, so it matters. And then we have call by value result. This is a modification of call by variable. When the procedure is called, the content of a cell is put to another mutable variable to local to the procedure. Yeah, I remember this. What is the use case of this?
The point is that
Transactional?
the point is that the mutation of the outer cell is only visible after you
Yeah,
return.
so it's transactional, this.
Kinda, yeah.
So you are creating a new cell that has the copy of the original, and you only apply the changes after you're done.
Yeah.
Yeah, so transactions, but in a language, like I don't know. This is I never seen this before outside of the scope of databases. So uh, now just for recording. Call by value result means that you create a mutable cell internally. You do the changes with the copy, and then you apply the changes to the one that matters at the end. That's
Yeah.
what this means. Yeah, and we have call by name. This mechanism is the most complex. It creates a procedure value for each argument. A procedure value used in this way is called a thunk. Each time the argument is needed, the procedure value is evaluated. So this is a very confusing shit because if you look at the name, call by name, we already seen this before. But it is just because in this language, the reference is the name. Uh,
Uh,
but this is different. So don't get bamboozled. This is talking about um, how should I say this?
Yeah, this is
Because
this is the algol calling convention, basically.
yeah, but nobody knows that language, so that's not helping. This is talking about
Basically Haskell, but if Haskell didn't do memoization of the
yes.
arguments,
No, no, no. Haskell doing memoization is the call by need.
which is a modification of call by name. That's literally the first thing it says.
Exactly. So we are essentially providing a way for you to get the value, but there's an extra step. So in NOS, the curly braces are function calls. So you don't have an A, you have something that when called gives you the A. Um,
Yep.
I don't see a use case for this. I do see a use case for this. Why would you do call by name if you have call by need? I don't know.
It's more primitive, I guess.
But it makes perfect sense, right? Because what this is doing is, again, taking what I said literally. You have a function that takes nothing and returns you the C. So when you're doing the SQR, before extracting the values, you need to call the function. You're gonna get the atom or the cell, you dereference, and then you need to do the reassignment on the same C, which means that you're calling the function 3 times. If you don't call the function 3 times and you were smart enough, you reach call by need. So that means that you're calling the function only once, and then you're doing everything else on top of it.
Yeah, and you have to be careful to only call it if you're actually going to use it, right?
Exactly. And there is a comment. Call by need is exactly the same concept as lazy evaluation. The term call by need is more often used in a language with state, where the result of the function evaluation can be the name of a cell. Call by name is lazy evaluation without memorization. The result of the function evaluation is not stored, so it is evaluated again each time it is needed. Uh, Actually, I take that back. There is a reason to not do this. Is if you're actually no, if you don't have enough memory, this is also bad because this is saving 3 times. This is saving once.
Um, if you don't have enough memory,
Yeah, that's not
if you
a
don't,
good argument. What would be the reason for you to not do memorization?
if you can't do memoization,
Yeah, if you don't have a cat, like if you can't do the lookups, maybe if you can't
like
do
what if,
memorization.
yeah, like if you're implementing laziness, but you don't have any mutation primitives, you are forced into doing call by name, basically.
Ah, that's fair. That's fair enough. Fair enough. Well, yeah. Okay, and then there's this discussion. Which of these mechanisms is right or best? This has been a subject of much discussion. The goal of the kernel language approach is to factorize programming language into a small set of programmer significant concepts. For parameter passing, this justifies using call by reference as a primitive mechanism which underlies the older mechanisms. Well, in this case, it's because this language uses a name for it. Unlike the others, call by reference does not depend on additional concepts such as cells or procedure values, which is fair enough. It has a simple form of semantics and is efficient to implement. On the other hand, it does not mean that the call by reference is always the right mechanism. For all parameter passing mechanisms can be coded by combining call by reference with cells and procedure values. Many languages offer these mechanisms as linguistic abstractions. Yeah, the book doesn't help because it doesn't define the metric for right. It has a good start, which is it requires less built-ins. That's a fair enough criteria.
Um, I guess another point would be because it doesn't depend on additional concepts, it's also disentangled from those concepts, right?
It doesn't what?
It's disentangled from those
It's
concepts,
disentangled.
so you can compose them later if you want, or you can just use it as it is.
Exactly. Yeah, so you can it requires less requirements to make those happen because for example, in the call by name, you need to use the function. You need to wrap it. In the call by need, you need mutability. In the call by value result, you need mutability. In the call by value, yeah, actually you can do this. Yeah, actually you can do this without mutability.
You Can, but only if you say, okay, actually you cannot mutate A, which is the same as just call by reference then, right?
You cannot mutate a. Yes, because then you would be using D in the math directly.
Yeah.
And then call by, this is called by value. Then call by variable, you have to mutate. And call by reference, you don't need any of that. So yeah, call by
Uh,
reference is kind of like a huge
yeah,
plus.
fun fact, Zig actually does call by reference technically because it
These
doesn't
call by
allow you.
reference.
Yeah, Zig actually does call by reference because it doesn't allow you to mutate the arguments, unlike C, which does.
Wait a moment. Zig doesn't allow you to mutate the arguments.
Yeah, if you give an
Ah,
argument
you need to
A
provide
to a
a pointer, a reference.
yeah, if you want your function to mutate quote unquote an argument, you have to say, okay, your argument is a pointer, do the mutation through the pointer. You can't even rebind the name of the argument because
Okay,
it's defined as a
that's a
constant.
very good point because this justifies the subtleties. Yes, yes, Zig doesn't allow that. That's true. Well, I don't. I'm not an expert on the language, but I believe you that they don't because when we did Lyceum, we only did references all around. We never mutated the names. Yes, such a tiny difference, but it does make everything different, right? Anyway, so we are done for today. 15 minutes over. That's understandable. So what are we gonna be doing next? So we stopped on 5.6.5. So
Collections, reasoning, program designing the large.
yeah, so it's all the way to 453. 453 for this is what? 15 pages. That's not a lot.
25 actually. No?
25? No, 15.
Yeah, 38. Yeah, no, it's 15. It's 15.
15. And then we should go one further. We go to 14, then 30 pages. But then we have a problem of the next time, right? Because the next time is gonna be 20 pages only. I think that's okay. So we can do 5, 6, and 7, and then next time we do 8 and 9.
Um,
What do you think? You read all of it, so you'll know more than me.
generating random numbers, limitations of stateful programming. Yeah, I think we could go either way, really.
No, the other
But
way is reading all of it. We're not gonna be able to do that.
no, there's the question of whether to include 6.7 or not, right?
Uh, ah, if we don't include 6.7, then it's gonna be 553 all the way to 587, which is 34 pages. Like the next time, the next. I don't know, 34 pages is a lot of pages, man.
Yeah, let's include 6.7. Why not?
Okay, and so it's gonna be 6.5 to 6.7, and then the next is gonna be 6.8 to 6.9.
Yeah.
Cool. I'm gonna finish the recording.